Okay, I'm just going to continue where I left off. Chapter 3, Common Programming Concepts. This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conversions around using them. Let me turn this down. We'll discuss them in the context of Rust and explain the conventions around using them. Specifically, you'll learn about the variables, basic type functions, comments, and control flow. The foundations will be in every Rust program, and learning them early will give you a strong core to start from. The Rust language has a set of keywords that are reserved for use by the language only. Much as another language, just keep in mind that you cannot use these words as names of variables or functions. Most of the keywords have special meanings, and you'll be using them to do various tasks in Rust program. A few have no current functionality associated with them, but have been reserved for functionality that might be added Rust in the future. You can find the list of keywords here. Variables immutability. As mentioned in the storing variables, values with variables section, by default, variables are immutable. This is one of the many nudges Rust gives you to write your code in a way that takes advantage of safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When the variable is immutable, once a value is bound to a name, you cannot change that value. To illustrate this, generate a new project called variables in your project directory. We're going to add a new folder called variables. And we're going to open and integrate under cargo, new variables. Okay. Then in your new variables directory, open the main RS and replace the code with the following code, which won't compile just yet. So we're going to replace this with let x equal 5 print ln the value of x is x equals 6 print ln the value of x is save and then try using cargo. Alright. Huh? Cannot find cargo tunnel. What? I'm confused. What? Am I not inside of there? Okay, I guess I'm in variables. I might have done that a little wrong, but we'll ignore that for now. Bound macro, value of x is not a function. Oh, I forgot that piece. Consider making this final. Cannot assign twice to immutable variable x. First assignment to x is 5. Cannot assign twice to immutable. But even when the program using cargo run, you should receive an error message regarding the immutability error showing this error. This example shows how the compiler helps you find errors in your program. Compiler errors can be frustrating, but really they only mean your program isn't safely doing what you want it to do yet. They do not mean that you're not a good programmer. Experienced Rustaceans still get compiler errors. You receive the error message cannot assign twice to mutable variables x because you try to assign a second value to the immutable x variable. It is important that we decompile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs. If one part of our code operates on the assumption that a value will never change, another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to. The cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler guarantees that when you state that a value won't change, it really won't. So you don't have to keep track of it yourself. Code is thus easier to reason through. But mutability can be very useful and can make code more convenient to write. Although variables are mutable by default, you can make them mutable by adding mute in front of the variable names, as you did in Chapter 2. Adding mute also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. For example, let's change src to the following. Let mute x. Now I'm going to run this program. Goes through fn main let mute x equal 5. Let the mutable variable x equal 5. Print the value of x is 5. And then now x equals 6. So print the value of x. Variable of x is 6. That's what I did. We're allowed to change the value bound to x from 5 to 6 when mute is used, ultimately deciding whether to use mutability or not. It is up to you, depends on what you think is the clearest in that particular situation. Declaring constants. Like immutable variables, constants are values that are bound to name and not allowed to change. But there are a few differences between constants and variables. The cat is First, you aren't allowed to use mute with constants. Constants aren't just immutable by default, they're always immutable. You declare constants by using the const keyword instead of the let keyword. And the types of values must be annotated. We'll cover types and types annotation in the next section, data types. Don't worry about the details right now. You just know that you must always annotate the type. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. The last difference is the const may be set only to a constant expression, not the result of a value that can only be computed at runtime. Here's an example of a constant declaration. Const 3 hours in seconds, unsigned 32 bits equals 60 times 60 times 30, 60 seconds, 60 minutes, 30 hours. The const name is 3 hours in seconds, and its value is set multiplying 60 number of seconds by 60 minutes by number of hours. Rest naming conversion for constants is to use all uppercase with underscores between words. The compiler is able to evaluate the limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify. Rather than setting this const to the value of 10,800, see the Rust reference section on constant valuation for more information on what operations could be used when declaring constants are valid for the entire time a program runs within the scope in which they were declared. This property makes constants useful for values in your application domain that multiple parts of the program might need to know about, such as the maximum number of points any player of a game is allowed to earn, or the speed of light. Naming hard-coded values throughout your program as constants is useful in conveying the meaning of that value for future maintainers of the code. It also helps to have only one place in your code that would need to change if the hard-coded value need to be updated in the future. As you saw in the guessing game tutorial 2, chapter 2, you can declare a new variable with the same name as the previous variable. I can say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any use of the variable name to itself until either it itself is shadowed or the scope ends. You can shadow a variable by using the same variable's name and repeating the last of the let keyword as follows. I'm going to write let x equal 5, let x equal x plus 1. Let x equal x times. Where is the star? I can't see because I don't have my lights on. Print ln the value of x in the inner scope is x. Print ln the value of x is the program first binds x to the value of 5. Then it creates a new variable x by repeating let x equal, taking the original value and adding 1 so that the value of x is 6. Then within an inner scope created in the curly brackets, the third let statement also shadows x, creates a new variable multiplied by 2. So 5 becomes 6, or 6. So now x is equal to 6. X equals 5. 5 plus 1 is 6. X equals 6. So 6 times 2 is 12. And so this is the inner scope. So the inner scope would be 12. The value of x outside will be 6. Inner scope multiplied by 12. When the scope is over, the inner shadow ends and x returns 6. When we run this program, it'll output the following. Shadowing is different from making a variable as mute, because we'll get compile time error if we accidentally try to reassign the variable without using the let keyword. By using let, we can perform a few transformations on a value, but have the value be immutable after those transformations have completed. The other difference between mute and shadowing is because we're effectively creating a new variable. When we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by inputting space characters. And then we want to store that input as a number. Oh, well, then do something. Let spaces equal 1, 2, 3. Spaces dot length. Oh, that's that one. The first spaces variable is a string type. The second spaces variable is a number type. Shadowing thus spares us from having to come up with different names. is space str and space num. Instead, we can reuse the simpler spaces name. However, if we try to use the mute for this, we get compiler error. The error says we're not allowed to mutate a variable type. So that's 1149. Get some water real quick. Remember, stay hydrated, guys. Every value in Rust is a certain data type, which tells Rust what kind of data is being specified, so that it knows how to work with that data. We'll look at two types, data type subsets, scholar, and compound. Keep in mind that Rust is a statistically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what types we want to use based on the value and how we use it. In cases when many types are possible, such as when we convert a string to a numerical type using phrase, in the comparing the guess to secret number section in chapter 2, we must add annotations like this. Not a number. If we don't add the U32 unsigned 32-bit integer type annotations shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know what type we wanted to use. Scholar type, scalar, I'm going to call it scalar type represents a single value. Rust has 4 primary scholar types: integers, floating points, number, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. An integer is a number without a fractional component. We use one integer type in chapter 2, the U32. This type declaration indicates that the value is associated with should be an unsigned integer. Signed integer starts with an I instead of a U. That takes up 32 bits of space. Table 3-1 shows built-in integer types in Rust. We can use any of these variables to declare the type of an integer value. My cat was sitting on me. 8-bit I8 or U8 for unsigned. Okay, makes sense. I don't know what architecture dependent is. Each variant can be either signed or unsigned and has an explicit sign. And unsigned refers to whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it, signed, or whether it will only ever be positive and can therefore be represented without a sign, unsigned. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume the number is positive, it shows with no sign. Signed numbers are stored within or are stored using two complement representation. My God. Where is dark mode? Yo, to be honest, I was gonna read this. I think it's a little long, you know. What? How does that make sense? Oh, okay. Each sign variant can store numbers from -2n-1 to negative 2n-1 to the 2 to the power of n-1 minus 1 inclusive, where n is the number of bits that variant uses. So an I8 can store numbers from -2 to the power of 7 to 2 to the power of 7 minus 1, which equals -128 to 127. Unsigned variants can store numbers from 0 to 2n to the power of n minus 1. So a U8 can store numbers from 0 to 2 to the power of 8 minus 1, which equals 255. Additionally, the I size and U size depends on architecture of your computer. If running 64 bits, is running on 64 bits if you're running 64 architecture, and 32 bits if you're running 32-bit architecture. You can write integer literals in any of the forms shown in table 3-2. Note that the number of literals can also use underscore as a visual separator to make the numbers easy to read, such as 1_000, which will have the same values if you specified 1000. Decimal X panel. So how do you know which types of integer to use? If you're unsure, rest defaults are generally a good place to start. Integer types default to I32, which primary situation in which you'd use I size or U size, in which indicating some sort of collection. And removal carries behaving Rust also has two primitive types for floating numbers. What? What? You're just staring at a wall meowing. What? 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 You're just gonna lay down? Uh-huh. And keep looking at the wall? And then you're shaking your tail. Boy, I don't know. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating points types are F32 and F64, 32 bits and 64 bits in size. What? You're still looking at the wall. Default type is F64 because on modern CPUs it roughly has the same speed as F32 but is capable of more precision. All floating point types are signed. Here's an example that shows floating point numbers in accurate common x equal to 2.0. What? Rust supports the basic mathematical operations you expect for all the number types: addition, subtraction, multiplication, division. cargo create new variable. Oh, I'm stupid. Data types. CD data types. Let's equal 5 plus 10. Location. Nope, I did that wrong. That's LN. What? The sum is cargo 1. Okay, so if we were to add the difference is difference the product. Can I enable word wrap? Is that an option? This is an option. Word wrap. The product is product. The quotient and the remainder the sum is 15, the difference is 91.2, and the product is 120 is 120. Yes. Question is whatever that is minus 1, and the remainder is 3. Alright. Let t equal true. As in other programming, Boolean types of true or false. Let f bool equal false. Let ln P is, does this work? God, I need a bigger keyboard. P is true and oh, I meant to make this F. Rust character type is the language's most primitive alphabet. Here are some examples of declaring character values. File name let b equal z. Oh, this needs a b. Let z char equal whatever. I don't know what in the world that is. But heart underscore hide underscore cat equal. Wait, you know? Cat. Yes. I have it. And I'll use the emoji selector. That's ln. The letter C is. This makes no sense, but we're gonna, in terms of writing, B. The letter Z is Z. And the variable heart underscore I cat is heart underscore hide underscore cat. Oops. What I oh crap. Oh crap. How did I forget that? I forgot to re-add it. C is Z. Note that though we specify char literals with single quotation marks as opposed to string literals, use double quotation marks. Rust char type is 4 bytes in size and represents a Unicode scalar value, which means it represents a lot more than just ASCII. Accented letter, Chinese, Japanese, or Korean characters, emojis, and 0 with spaces are all valid character values in Rust. Unicode scalar values range from U plus 0000 to U plus D7FF, U plus E00, and U plus 10FFFF inclusive. However, a character isn't really a concept in Unicode, so your human intuition for what a character may not match up. What a character is that. Okay. My intuition for what a character is may not match. Intuition for what a character may not. Okay, so maybe there's a typo in the book, guys. Maybe I just don't know how this works. Not match up with a char and is in Rust. We'll discuss the topics in detail in storing UTF-8 encoded text with strings in Chapter 8. Who the hell is Chris? Oh my god, my cat wants out. My headset back on. Chris kind of got some bops. Compound types. Compound types can group multiple variables values into one type. Thus has two primitive compound types, tuples and arrays. The tuple type. A tuple is a general way of grouping together a name of values of a variety of types into one compound type. Tuples have fixed length. Once declared, they cannot grow or shrink in size. We can create a tuple by writing a comma, separate a list of values inside parentheses. Each position in the tuple has a type. And the types of different values in the tuple don't have to be the same. We've added optional type annotations in this example. Let tup I32 F64 U8 equal 100 6.4 1 13 Let's LN. Current tuple is tup. Does this even work? Will that even print out what I want it to? Cannot be formatted with the default formatter. I see. Oh, it explains at the bottom. So we can let, okay. So if we let's, or we can't do let, we can do let x. Let's x, y, z. We cannot do that. X, y, b do equal to. The current tuple is x, y, b. Does this print out? 506.411. The program first creates a tuple and binds it to the variable tup. It then uses a pattern which lets to take tup and turn it into three separate variables. This is called destructuring because it breaks a single tup into three parts. Binding the program prints the value of y, which is 6.4. Okay. You can also access tuple element directly by using a period. I'm not sure I understand. The program creates a tuple x and then accesses each element of the tuple using the respective index. How do I say this? Is that really just
index?
Is that really just index? Indices, bro. Index. For the first. Okay, bro. As tuple using respective indexes. As with most programming languages, the first index of a tuple is 0. This value and its corresponding type are both written in parentheses and represents an empty value or an empty return type. Expressions implicitly return the unit value if they don't return any other value. the array type. Another way to have a collection of multiple values is with an array. Unlike tuple, every element of an array must have the same type. Unlike arrays in some other languages, arrays in Rust have a fixed length. We write the values in an array as a comma-separated list using square brackets. Let A equal, use square bracket, 1, 2, 3, 4, 5. Arrays are useful when you want your data allocated on the stack the same as the other types we have seen so far, rather than the heap. We'll discuss the stack and heap more in chapter 4, or when you want to ensure that you always have a fixed number of elements. An array isn't as flexible as a vector type, though. A vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size because its contents live on a heap. If you're unsure whether to use an array or vector, chances are you should use a vector. Chapter 8 discusses vector in more detail. However, arrays are more useful when you know the number of elements will not change. For example, if you were using the names of the months in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. Let me copy this. Boop, boop. That did not. Well, it's its word wrap. I'm stupid. But if we do broink, yeah. You write an arrays type using square brackets with the type of each element, a semicolon, and then a type, then the number of elements in an array like so. Here, I32 is the type of each element. After the semicolon, number 5 means it contains 5 elements. So, there can only be 5 elements under the integer of 32-bit. Alright. You can also initialize an array to contain the same value for each element by specifying the initial value followed by a semicolon, and then the length of an array in square brackets, as shown here. The array named A will contain 5 elements and will be set to the value of 3 initially. So, writing the same as let A 3333, but in a more concise way. An array in a single chunk of memory of a known fixed size that can be allocated on the stack. You can access elements of an array using indexing like this. First A, second. So we're taking the A array, we're taking the variable 0. Number 0, 1, 2, 3, 4. The variable named first will get the value 0 because value 1 because this is the value at the index 0 in the array. Second, get the value 2 from the index number 1 in the array. So if we make, I guess we could probably delete all this now. Have been made. Okay, we need to do use std boink. Let A equal 1, 2, 3, 4, 5. Print ln. Please enter an array index. Let mutability index variable for string new input user input stdin string dot read underscore line and wherever the and it no put the and all the way over number 8 or number 7 index dot expect fail to read line. So we're expecting to fail to read line. Double tapping. Index is not how you spell index. U size index. Trim. Trim. Effect. Oh, I did not realize that was a thing you could do. Maybe I did. Index entered not a number. And elements equal a index. Print ln the value of the element at index is outlaw. One. Oh, cargo. L. Oh. Oh, maybe not. Then I use this right here. Huh? What? How did I not use this? Somehow, what? Okay. Apparently I did something. No, I don't think this is it. Is that it? No. How is this not used? What? A. Oh, I said get A. Oh my god. Five, but the index is 5. Index out of bound. Program resulted in a runtime error at the point bound value in the indexing operation. The program exited with an error message and didn't execute the final println statement when you attempted to access an element using indexing. Rest will check that the index you've specified is less than the array length. If the index is greater than or equal to the length, Rest will panic. This check has happened at runtime, especially in this case because the compiler can't possibly know what value a user will enter when they run the code later. This is an example of Rust memory safe principles in action. In many low-level languages, this kind of check is not done. When you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. Chapter 9 discusses more of Rust error handling, how you can write readable safe code that neither panics nor invades memory access. So, oh boy, 50 minutes. I'm probably gonna cut it off for right now. I'm kind of doing this at my own pace. Like I said, it's kind of just for me. It's 12:25 a.m. So I mean, probably gonna go to bed soon. Before I get this uploaded. So I'll continue on at functions here. I changed my code editor, or the actual using coding software, VS Codium. So there's that, I guess. Bookmark this. Functions. And let me build dash release. So yeah, this is probably what I'm cutting off right now. Like I said, this is just mainly for me. I'm kind of want to just do stuff on my own. I do have 2 videos planned probably for tomorrow. Probably get both of them out. They'll be for the new Wabbajack setup and Jackify. So there's that. Anyways, I mean, if you're still watching at this point, I hope you guys did enjoy. I mean, there's not much really to enjoy other than me watching, learning how to code. If that's what interests you, hey, not to complain, but hope you guys have a nice night and see you.